So the last thing we're going to look at here is a sense of how quickly something can move on a circular path. That is linear speed, where if we have an object that is moving along a circular path, something like so, we both have to consider how quickly it moves along that path, as well as how quickly its rotational position, its angle, changes when we're going to talk about its speed. So we have both the idea of linear speed, where that's just the value v equals s, the length, its change in position over time, where that value s for the arc length, like before, is r theta. So speed in this case is r theta over t. And then angular speed, that is how fast its rotational position adjusts, which is given by the Greek letter omega. That's an omega, not a w, even though I am sure that I will get that wrong at some point this semester. But it is equal to theta, the angle, over t. So how much the angle changes over time. But the nice thing here is we have omega equals theta over t, where v is r times theta over t. So we can talk about the linear speed, the change in position like so, as being the product of the radius, which is not a changing value. The radius is always going to be the same for this, multiplied by the rate of change in the angle, which is omega. So we have that linear speed in terms of angular speed is r omega. And to understand this, we're going to look at a quick example, where here we have that a motorboat engine has a 7-inch blade that rotates at 5,400 RPM, where we want to find the linear speed in the tip of the blade in inches per minute. So here, let's just take down some of the information we have, because we're going to be doing some unit conversions. We're going to say that r is equal to 7 inches. It's a bit of an unfair assumption, because you actually have the center of the propeller sometimes, depending on the design, but we'll just say it's 7 inches the length of the blade, because that makes our life a little easier. And then we also have the angular speed here, omega, is given as 5,400 RPM. And 5,400 RPM, that's a really useful measurement for an engine, but if we're trying to find out how fast it's moving in terms of a changing position, that's not very useful. So we want to convert that 5,400 RPM into something in terms of the angle it covers. Well, 5,400 RPM is 5,400 total revolutions per 1 minute. Okay, then we can understand that 5,400 revolutions can be reframed in terms of how much space that takes up on a circle. That is, a full revolution is covered by 2 pi radians. So if you want to cancel out revolutions, we can do it like so to reframe our measurement in terms of radians, getting that the angular speed would be 10,800 pi radians per 1 minute. And now we have our angular speed in terms of an angle. We have our radius, so we can get our linear speed. That is, s is equal to 7 inches multiplied by our speed here, 10,800, oh boy, radians per minute. which here will give us a somewhat large-looking value of 75,000. Gotta say that clearly. Get all of my zeros in there. 600 pi radians. Actually, not even radians anymore because we're multiplying in those radial values to just turn it into inches per 1 minute. Or if you prefer to get that pi out of there, it would be approximately 237,504 inches per minute. Which seems to me like that'd be quite fast, but, well, rotational speed was never my greatest strength in physics. Still, seems significant. And that's all we're going to see here for 4.1. Next, we're going to move into 4.2, where we're going to try and generalize these angular behaviors, as it were, towards a construction called the unit circle, and then use that to build into our work with trigonometry. And yeah, I know trigonometry is not the most exciting thing in the world for a lot of people, but it's important stuff that we're going to be seeing a lot of for the next couple of chapters, starting soon.